Hello, everyone. My name is Eleonora Isotta, and I'm a postdoc at Northwestern University, working with Professor Jeffrey Snyder and Professor Oluwaseyi Balogun. And in this video presentation, I'm going to talk about our recent article entitled Microscale Imaging of Thermoconductivity Suppression at Grain Boundaries. So grain boundaries suppress the thermoconductivity. This is a very well-known phenomenon, and is thought to occur because grain boundaries introduce a source of scattering for heat carriers. And the effect of grain boundaries can be quite significant. For example, this is the thermoconductivity of silicon, and you can see that at room temperature, the thermoconductivity can go from values around 150 watt per meter Kelvin for a single crystals down to values in the order of 30 watt per meter Kelvin when a grain size in the order of hundreds of nanometers is introduced. So for this reason, grain boundaries were one of the earlier strategies that was proposed in thermoelectrics to suppress the thermoconductivity that can overall lead to an enhancement of the figure of merit ZT. For example, these two are two very famous works in our field where they have shown in silicon germanium that introducing a finer grain size was overall conducive to a higher ZT as compared to single crystals or bulk materials with an overall higher grain size. And in the last 2 decades of thermoelectric research, really countless are the studies that have employed grain boundaries or some other forms of nano or microstructuring to suppress the thermoconductivity. So grain boundaries are a really well-known and exploited mechanism. However, in the thermoelectric field, we usually measure bulk properties. And so therefore, what we usually do is effectively treat the sample as homogeneous and extract the effect of grain boundaries by looking at how bulk effective properties change as a function of grain size or grain boundary type. Instead, we don't really have a good understanding of what happens locally in the vicinity of the grain boundaries. And this would be quite important if we want to leverage grain boundary engineering to overall improve the thermoelectric properties. In this direction, a very interesting study coming out a few years ago was this one where they employed time domain thermoreflectance, or TDTR, to map the local thermoconductivity in a polycrystalline diamond sample. And they realized that the thermoconductivity is not homogeneous at all, but in fact, in regions with a high density of grain boundaries that were identified with electron backscatter diffraction, or EBSD, they noticed that the thermoconductivity was roughly 50% suppressed as compared to the center of large grains. As I said, this study was made with polycrystalline diamond and is pretty unique in the literature. And diamond with a bulk thermoconductivity of 1000 watt per meter Kelvin is pretty different than regular thermoelectric material, which usually has a much lower thermoconductivity. So for this reason, we thought, can we use a similar methodology to study possibly individual grain boundaries in thermoelectric materials? And with this, hopefully get a little bit of understanding of how grain boundaries work in thermoelectrics and how can we use them to achieve our goal of overall improving the properties. So this is exactly the object of the present study. So as material, we have chosen tin telluride because it's a quite good thermoelectric with a simple crystal structure and a relatively high thermoconductivity to be a thermoelectric material. And additionally, there's a reported marked effect of grain boundaries in the system in the literature. And we have synthesized the sample with a melting and very slow cooling technique, such as so that to obtain grain sizes in the order of hundreds of nanometers that would allow us to measure across individual grain boundaries. And the room temperature thermoconductivity is around 8 watt per meter Kelvin. For the thermoconductivity imaging, we employed a technique of frequency domain thermoreflectance, or FTTR, which is somewhat similar to the technique of TDTR that was employed for polycrystalline diamond. So in this method, we'd first locate the grain boundaries with EBSD. Then the sample is coated with a very thin layer of gold that serves as transducer layer for FTTR. In fact, FTTR is a pump probe technique making use of a pump and probe laser. So a pump laser that is frequency modulated is focused on the sample and is used to locally heat it up. The change in temperature will induce a change in reflectance in the gold layer. And this change in reflectance is monitored by directing another laser called probe laser on the same spot. And there will be a phase difference between the input power from the pump and the actual heating that is measured by the probe. And this phase difference will depend on the heat conduction capabilities of the underlying sample. So by fitting the phase between pump and probe to a heat conduction model, we are able to extract the thermal conductivity of the underlying sample as a fitting parameter. And then we repeat the measurement by raster scanning over the interested area on the sample with a step size of 3 microns. And we overall image areas of 100 by 100 microns. Okay, so this is the EBSD that we have conducted on our tin telluride sample. As you can see, the grains are in the order of hundreds of nanometers. And this is the thermal conductivity imaging that we have performed in the areas marked by the squares on the left image. So as you can see, we do see some suppressions of thermal conductivity that correspond to the locations where we would expect grain boundaries to be according to the EBSD image. What we can see is that the suppression of thermal conductivity is in the order of 0.5 to 1 watt per meter Kelvin, while the background thermal conductivity of the sample is around 8 to 8.5 watt per meter Kelvin. So reasonably in line with the bulk measurements that we performed earlier. And we can see that this suppression, interestingly, has a width of roughly 10 microns. So one very first thing that we can comment about these results is that the picture that we would derive from the FTTR measurements is quite different from the picture that we would think of grain boundaries when we use traditional models. For example, in thermoelectrics, we are used to think of thermal conductivity with Callaway-Clemens models, where the lattice thermal conductivity is the integral over phonon frequency of the heat capacity, the phonon group velocity squared, and the phonon scattering time, for which we normally use the Mathiesen rule to combine different scattering mechanisms. So when we have boundary scattering, the boundary scattering term is proportional to the grain size. And this is effectively the assumption that we're making in this formula here is we are assuming that the grain size will set a limit to the maximum phonon mean free path that is allowed in the system. And this limit is equal to the grain size. So as such, a model of this kind will predict a grain size dependence of the thermal conductivity, with smaller grains producing overall a lower thermal conductivity. But then this value would be homogeneously applied to the overall sample. Instead, what we are getting from FTTR is that the thermal conductivity is not homogeneous at all, but it does vary locally in a region around the boundary. And the other interesting thing that is quite different from the usual literature treatment is that different grain boundaries behave differently. And this is quite easy to see, for example, if you look at this area A1, where we can clearly see that the central grain boundary has a lower thermal conductivity suppression as compared to the top or the bottom boundary. And we think this has to do with the grain boundary misorientation angle. In fact, the central one is a low angle grain boundary, while the other two are high angle grain boundaries. And this would be in accordance with the dislocation model of grain boundaries. What is this? So according to the model developed by Rudd and Shockley, a grain boundary can be seen as an array of dislocations. So you can easily see in this figure here that whenever we have a crystal and we introduce a misorientation like they do here on the right, some atomic planes are geometrically required to terminate at the boundary, thus effectively forming a dislocation. So the higher the misorientation angle, the denser is this array of dislocations. And this is also at the origin of the increase in grain boundary energy with grain boundary misorientation angle. And there are some literature studies that actually show that the thermal resistance of grain boundaries, also known as Kapitsa resistance, should be correlated with the grain boundary energy. So should also increase with the grain boundary misorientation angle. But in order to compare our results with theoretical results from the literature, we need a way to extract an equivalent thermal resistance from our thermal conductivity measurements. To do so, we have employed a Gibbs excess approach. In short, if we make a cross-section at a grain boundary, the thermal resistivity, that is the inverse of thermal conductivity, is expected to be constant in the grain, then locally increasing at the grain boundary, and then constant again in the grain. So we define our excess boundary resistance as the excess resistivity that is produced by the grain boundary. So as the integral along the direction perpendicular to the boundary of the local thermal resistivity minus the constant value in the grain. So we have employed this method to extract the boundary resistance of all the grain boundaries that we have imaged. And we can indeed see that low angle grain boundaries tend to show a lower boundary resistance as compared to high angle grain boundaries. The trend is not clean and linear though, suggesting that likely other phenomena are at play. To verify the validity of these estimates and the soundness of the Gibbs excess approach in extracting value of boundary resistance, we have employed an effective medium model, where in this model, we treat a polycrystalline sample as a series of the contribution of grains and grain boundaries, where for the grains, we use a value of thermal conductivity of a single crystal, while for the grain boundaries, we use the average value of boundary resistance from FDTR as a representative boundary resistance. And with this model here, we would predict grain size dependence of the thermal conductivity that trends as the black line in this figure here. And we can see that we find quite good agreement with thermal conductivity values measured for some polycrystalline samples that were independently synthesized and measured. So this suggests that the Gibbs excess method might indeed be appropriate to extract an equivalent Kapitsa resistance for grain boundaries from the thermal conductivity imaging. So in summary, we have seen that the FTTR seems to be a suitable technique to measure the thermal conductivity and to perform thermal conductivity imaging of grain boundaries in thermoelectrics. And we have seen that by employing a Gibbs excess approach, we are able to extract an equivalent Kapitsa resistance for the grain boundary that shows us that there's a trend of thermal resistance with misorientation angle in tin telluride. And with this, I would like to thank all the people that participated in the work. And I would like to thank you for the attention. And if you have any questions or comments, please don't hesitate to email us. And if you're interested in the full text article, I will leave the link to the website of the journal in the description box below. Thanks again for the attention.